Thank you very much. Thank you very much for being here, all of you, and thank you for the organizer for allowing me to present these works. This series of works that I've been doing with my supervisors here in Bologna, Michele Ciccoli and Francisco Pedro, and with my collaborators Filippo Revello and Gonzalo Viglia. Now, the first question that must be answered is why cosmic strings? So, why are they interesting and why do we care about them? Well, cosmic strings are these one-dimensional objects emerging in various BSM theories, and being a BSM theories and having strings in their name, they also appear in string theory. And in particular, we are interested in cosmic string networks. And cosmic string networks can form either at the end, say, of a very energetic process like brain anti-brain annihilation at the end of inflation, for example, or from closed strings that grow in comoving size and percolate into a network. Now, once a network forms, it reaches a scaling regime where it stays a constant fraction of the energy density of the background while constantly emitting gravitational waves through loop chopping, as we will see in a moment. And in the scaling regime, basically, if you manage to track these gravitational waves, the spectrum, throughout the history of the universe, well, you can get a lot of information about the cosmological evolution. Now, the outline of this talk, I will divide it in roughly in two parts. The first one, I will talk about the formation of this network, a process that can lead to a formation of this network. And in the second, once the network is formed, I want to put some bounds on the allowed spectral index of the gravitational waves from it. So, first of all, let's start from a Namu-Goto action with a space-time dependent tension. We want to vary this action, and we do it in an FLRW flat, spatially flat FLRW space-time, and we take a circular loop ansatz for the moment just to set the ideas. And after doing that, we gauge fix it to get an equation of motion. Actually, we get two, but this is the most interesting for us, that it ties the proper length of the string, the variation of the proper length of the string, to the variation of the tension in time. Now, the string grows in comoving coordinates if it's the growth of its proper length is, let's say, it grows faster than Hubble. Now, going back to this equation, you can see that this happens when this term here is negative. And this is what in this paper here was found by Joe Conlon et al. And when this term is negative, you get a growth condition. These loops grow in comoving size and they get closer to each other. And therefore, they can at some point touch and percolate and form a network. Now, suppose now that the time dependence of this tension is set by a scalar field, by the dynamics of a scalar field, homogeneously, spatially homogeneous scalar field, and this tension has an exponential dependence on this field. Now, if you plug this in the previous equation and change into number of e-folds as a time variable, you get this, which clearly links the dynamics of the field to the growth of the loop. So we can study the dynamics of the field to get information about the growth. So let's do it. And first of all, the setup of the dynamical system will have a background fluid with equation of state omega. And for the moment, we will neglect the energy density in loops. The space-space variables will be x squared, which is the fraction of the energy density of the universe in the kinetic energy of the field, and y squared, which is the fraction of the energy density in the potential energy of the field. And we will take an exponential potential also for the moment. Now, plugging everything in the Klein-Gordon equation and the continuity equation, we get this autonomous system for the two variables in number of e-folds, which was studied in this paper by Copeland, Liddell, and Wons, and its fixed points are fully categorized. In particular, the fixed points are when we set this x prime and y prime to 0. And what we find is that this is the phase space, first of all, the allowed phase space for the system. And then we have the kinetic fixed points, which are whenever the energy density of the universe is fully dominated by the kinetic energy of the field, the fluid domination where it's fully dominated by the background fluid, the field domination where all of the energy density is in the field, but it's in a constant fraction of its kinetic energy and potential energy. And finally, the most interesting of all, the scaling fixed point or Tucker fixed point, where the energy density of the field tracks the energy density of the background. And this fixed point is always stable whenever it exists. Now, if we plug the phase space variables into the growth condition we found before, these, let's say, delimit a growth region in this phase space, which is a section of that semicircle I showed you before. And it depends on the sign of psi, but both of these conditions tell us that if we want a growth region in phase space, this psi, so the dependence of the tension on the field, must be at least square root of 2/3. Otherwise, we have no growth region because the tension does not depend enough on the field. Now, can we push some of, provided this growth region exists, can we push some of this fixed point within this growth region? Turns out we can, depending on psi, lambda, and omega. K plus and K minus can all, either one of them, can always be in the growth region, and M and S depend on the various values. Now, let's be more concrete, but to be more concrete, let's fix a scenario that we want to analyze. And in particular, the scenario I have in mind when I'm talking to you about this is this. We have a scenario of string inflation that takes place at very high energies. It can be brain-anti-brain inflation or an inflection point inflation for the volume modulus, something like that. We don't care, okay? After inflation, either the inflaton field or a spectator field starts rolling down a steep exponential potential, which leads to a low scale minimum, and it can traverse also a long field range, okay? Long meaning tens of M Planck, okay? Now, in particular, if we embed it in type IIB string theory, we see that in the EFT of string theory, there is no free parameter, and being the tension of the these cosmic strings a parameter, these must be set by the compactification moduli, by the VEV. Now, for fundamental strings, for example, the tension is set by the string scale squared, which depends on two moduli in Einstein frame. In particular, we have the volume of the compactification manifold and the dilaton, the canonically normalized dilaton through the string coupling. Now, if we focus on the dependence on the dilaton, we immediately see, and fix the volume for the moment, we see that the psi is too small and we never have a growth region in the phase space of phi. On the other hand, if we fix the GS, so the dilaton, and move along the volume direction, upon canonical normalization, we find that psi is actually larger than this square root of 2/3, and therefore there is a growth region in its phase space, which is this circular sector here that I highlighted. And of course, the kinetic fixed point is in it, okay? And this is the result of the paper by Joe Conlon et al., the seminal work on these cosmic string loops. And in particular, since if we take a perturbative potential for the volume, which goes as 1/v to some power, this again is an exponential potential. So we can use all of our dynamical system techniques. And in particular, if we start close to the kinetic fixed point, even if it is unstable, we will stick close to it for a long number of equals before moving out of the growth region. And in particular, the closer we are, the longer it is the time that we are inside, and the longer it's the time that the loop can grow. Moreover, the other fixed point, like M and S, can be pushed inside. So M can be pushed inside if the potential is sufficiently steep. However, if it's too steep, this fixed point is unstable. While for S, if we have the right balance between the equation of state of the background and the slope of the potential, this S can be pushed inside the growth region, and this is stable. So the field will spiral around it for as long as the exponential approximation is valid. Now, F strings are not the only kind of strings that we have in FT of string theory. We can also have E effective strings, which are P branes wrapped around P minus one cycles, compactifying the action of these P branes on this P minus one cycle. We get the tension of this effective string that depend on the volume in string units of the internal cycle. And this gives us an additional modulus dependence. In type IIB, this can be either D3 branes wrapping a two cycle, or NS5 or D5, depending on the orientifold you choose, wrapping a fourth cycle. Now, in a simplest case, where the volume is just a two cycle cubed, this allows for no growth region for effective strings. For D3 strings, the condition is marginally satisfied, while for NS5 strings, these shrink in comoving radius. While if we move away from the simplest case and go to the next to simplest case, let's say, like a Calabi-Yau with a fiber structure, this is no longer the case. Indeed, if we have like a P1 base fibered by a T4 or a K3, the volume takes this form, where T1 is the volume of the base and T2 is the volume of the fiber. Now, and this is in terms of four cycles. Now, the idea would be, let's keep the volume fixed, as we have seen that this does not lead anywhere. And let's move in the orthogonal direction of field space. And this orthogonal direction is given by this U. And if we check the canonical normalization of these fields, since the tension is linear in the wrapped cycle volume, we can check just the canonical normalization of these two, and we can see immediately that this is the fiber for cycle and this is the base to cycle, that indeed the tension has the right dependence. So psi is larger than square root of 2/3, and therefore we have some groove regions in the respective phase spaces. And notice these are just mirror of one another. In particular, these are this is the growth region for a fiber for cycle. This is the growth region for the base to cycle. Okay, these are just one the mirror of the other. Again, if we take a perturbative potential for the fiber, like loop generated or something similar, we get that we can use the dynamical system approach that we used before. We have the same autonomous system, and the kinetic fixed points are in the growth region since they exist. And without diving too much into details, again, the M and S fixed point can be pushed inside the respective growth regions. So effective strings and F strings can grow in comoving size, and at some point they could percolate into a cosmic network. Now, before moving to the gravitational wave part, let me take a break, a moment, and relax some of the hypotheses that we made. So in a paper that we of 2025, Noelia, Sanchez Gonzalez, and Joe Conlon et al., they relaxed the hypothesis that the loop do not contribute to the energy density, and they included this loop contribution to the energy density in the dynamical system. We just include this Z squared inside the dynamical system, and we suppose no background fluid for the moment, so we can eliminate this Z squared in favor of this X squared and Y squared. Now, including these loops, we get a dependence on this beta, which is psi, basically, inside the dynamical system itself, the autonomous system itself. And this gives us a new attractor solution, which is a loop tracker. This loop tracker is interesting because the energy density of the universe is split between the kinetic energy of the field and the loops themselves, while the potential gets zero energy total. So what we get is that the loops can grow to become a large portion of the energy, depending on beta, a large portion of the energy density of the universe. In particular, for F strings, where beta is 1/2, they make up 75% of the energy density of the universe as long as the field is on the tracker. However, as you can see here, in a realistic potential, the field is bound to overshoot the minimum because it moves too fast when it approaches the minimum. In particular, let's take an LDS potential, which is thus a potential for the volume modulus generated by integrating out a small field and uplifting it. What we get is that we have a very steep exponential potential on the left, and then we have a shallow maximum. So if the field races down the minimum, this slope of the potential, it will shoot over this maximum and go to infinity in a decompactification limit. Now, for F strings, if we include these F strings in the dynamical system, the field always overshoots the minimum, no matter what's the initial condition and how many strings you have at the beginning. However, since beta is lower for effective strings, what you get is that also x squared, the fraction of energy density in kinetic energy, is lower. So the field is actually slower when it gets to the minimum. And indeed, if you have these 5 strings and 5 strings, you can also have that the field does not overshoot the minimum and it settles to its late time minimum, since these absorb the energy more efficiently. Okay, so now let's move really to the gravitational wave part. So first of all, let us bound the possible time variation of the tension. To do that, I will use a concept which is the species scale, which for us will just be an upper bound on the quantum gravity cutoff of the EFT. Okay, we'll just use that to represent that. Now, for the emergent string conjecture from the Swampland program, any asymptotic limit in moduli space can be read either as a decompactification limit or a tensionless string limit. So either one of the dimension or more of the dimension become large, or the tension of the string is going to zero, ms is going to zero. In respectively, ls in these cases can be identified with the higher dimensional Planck mass or the string scale. So it makes sense, since the quantum excitation of these F strings and effective strings have to lie outside above the AFT cutoff, it makes sense to always put this bound on mu. The tension must always lie above ls squared. And this is the case in these two cases that I showed, because mu is either ms squared for F strings, or is ms squared times a volume which is larger than 1. So basically, this always holds for us. Now, and this was also found in various other works on the topic. And if we bound the variation in time of the species scale, we can in turn bound the variation in time of mu. And this is what we did in our most recent paper with Filippo Revella and Gonzalo. Now, the time variation of the species scale can be bounded using Cauchy-Schwarz with the field space variation of the species scale times the modulus of this vector times the modulus of the vector of the velocities of these fields. Now, this one can be bounded in a decompactification trajectory. So when, let's say, the volume of a cycle is becoming large, from d to d plus k dimension, it can be bounded like so, and this was found in this paper by Van die Heijsteg, Waffa, and Wiesner. And for d plus k less or equal than 10, this is the final bound for the theory, where d is the dimension of the effective theory. Now, this one instead can be bounded in 4D, for example, when you have a power loss scale factor and an equation of state omega. You can integrate the second Friedman equation to get a bound on d phi I on dt on a scaling solution. And what you get is this, where this n is the dependence on the scale factor on time, and this omega f is just the fraction of energy density of the fluid. And as you can see, this is smaller or equal than square root of n times h, if this is 0. Now, integrating these bounds and supposing that the tension goes as t to the minus q, we can get a bound on q due to the inequality we had before, as q smaller or equal than square root of 6 over n in any decompactification trajectory. Now, how do these cosmic strings generate gravitational waves? So these cosmic strings are long extended objects. They self-intersect or intersect among each other, and they chop off smaller loops. And these smaller loops oscillate, and oscillating they evaporate in gravitational waves. And since these strings are always intersecting and chopping off these loops, this emission is a continuous process in time. Now, if we suppose that the tension, that the time dependence of the tension and the scale factor does not change in this in a time interval between t1 and t delta, say, we can compute the gravitational wave spectrum on observed frequency f today in this way, using this integral, where this is the redshift of the gravitational wave itself. This is the emission power of the gravitational waves, which is proportional to g times mu squared. This is the redshift of the initial population of loops to the time of emission. And this is just a factor accounting for how many, say, the loop formation rate and emission frequency. Okay, you can recast this integral as a function of f, and at the end of the computation, you will find that it goes as f to the a, and this a is called a spectral index. Now, without diving into much details, you can separate, say, this computation into different domains, okay? And in particular, the most interesting part is that all of this section of the parameter space, we have q and n here, which is the time dependence of the tension and the time dependence of the scale factor. This is excluded by our previous bound on the time variation of the tension. So you cannot lie here, okay, in any effective field theory of strings. Now, in this part here, the loop emission is dominated by the early times, the formation times, and what you get is this formula, this nicer formula for A, while in this case here, you have a peak when the loop has emitted half, more or less half of its energy in gravitational waves. And this is an uglier formula, but still we will treat it nicely. And finally, in this part here, higher modes, more than the fundamental one, contribute to give you an A of minus 1/3. Now, we have different formulas of the scale of the spectral index, but we can see that this one at fixed n, so moving vertically on a given n, is a monotonically increasing function of q, which means that any A in this column here is bounded by an A in this column here, which means that this will be always lie below this one for the allowed range. And therefore, by bounding this one, we bound every possible scale factor. And in particular, using our bound on Q and N, we get that A should always be below this expression for a given N. So given a background, we know that A cannot be larger than a certain amount. Now, this one is saturated, for example, by volume mode declination for F strings, okay? So if the time dependence of the tension comes in, so if you have F strings and the volume is kinating, the time dependence of the tension gives us Q equal 1, and since it's kination, N is equal to 6. So we are here. And in this case, A is equal to 4. Now, notice one interesting thing, that when Q is equal to 1, this A is always equal to 4, okay, independently of the equation of state of the background. So therefore, on this line of Q equal 1, A is always equal to 4. So this is a more general behavior than just volume kination in F strings. And we can find for effective strings other examples in which this behavior is achieved. For example, we can have effective strings with fields on trackers of particular potential. For example, we can have D3 strings wrapped around the base 2 cycle on a radiation or matter tracker independently, And this is the overall potential is generated by a KK loop correction on the fiber cycle associated to this base 2 cycle. This is the form of the potential. On a track, this is how the field behaves. And by doing this computation, you find that mu is indeed going as 1 over t, and A is exactly equal to 4 here. So let me conclude. So both F strings and effective string can grow in comoving size, even if not inclination. Effective string may prevent overshooting of realistic minima since they act as a friction field. The time variation of the tension of cosmic superstring can be bounded by Swampland criteria, and the spectrum is also bounded by the same criteria. And finally, for mu equals to 1, going as 1 over t, the gravitational wave spectrum goes as f to the 4 independently from the background. And we can find various examples, both with f and effective strings. So there are a number of possible directions. For example, how do we produce this initial population of strings that grows? And this is important to estimate their number density to get the correct gravitational wave spectrum. We can analyze the emission of gravitational waves in correlation of the dynamical system as well, how it modifies or doesn't modify the overall system. And can these interact? So we suppose these are all separated loops. Can they interact? How does it change the behavior of the network and the behavior of the system, the dynamical system as well? And then we can also try to compute the couplings and therefore the spectra of other light species like axions or moduli themselves. Thank you for your attention.
Thank you very much, Luca, for the very nice talk. Any questions for Luca? Maybe I can ask like a super naive question. When do you expect results? I mean, like, what's the timeline for like seeing gravitational wave results from experiments that one can really start?
This is, I mean, so the frequency, the typical frequency of these gravitational waves goes as 2k, which is the harmonic, say, so 2 over the length of these loops. So these loops, when they are chopped out, these are very small, basically. And what you get is that these are very high frequency gravitational waves. In principle, though, this A equal 4 behavior gives you, it means that you have a growth of these omega gravitational waves towards larger frequencies, okay? Still, they are very large frequencies, and we have currently no experiment in those ranges. So it's wishful thinking for now, but it's nice to have it, for the future.
Yes, I agree. Thank you. Okay. Any other questions for Luca? If not, we can thank both the speakers again. And let me pause the recording.